Well, welcome to part 6 of the never-ending series on the Marantz 2252B. Hopefully this will somehow be the last video. And for this video, I think we will all be serenaded by my wife, who has decided to go back to playing the flute that she hasn't touched since high school at the coaxing of my daughter and one of her best friends. So enjoy the music from someone learning flute all over again while we do these tests. Okay, I hope I have this set up properly so you can see it. I have some of the lights turned off, but this one here still got some glare to it, but I think you can see the scope. So what we're going to do is we're going to do our max power THD test once again. And I had a couple of comments about where you connected the distortion meter, how, I had it was convoluted looking and it's affecting it. So let's just see how much it affects it. So I have this connected the way I did on the last video. And what we have is the THD meter connecting over to here to my breakout box. And all this is just several connector jacks that go directly to the coax that goes over there. You can't quite see it back here, but my dummy resistor load back there. And all it is just paralleled to that. So anything connected to these connectors along here are all in parallel. And so let me go back here. And again, we're supposed to have about 0.05% THD at 1 kilohertz at maximum power with both channels driven. And let's see if we get that. So right there's 10 watts, 20 watts, 30 watts, 40 watts. We're at our 0.05. So I think it's going to go a little bit over, but again, we have we have a bunch of wiring and things in there too. And there's your 50 watts or 52 watts, and you can see it's about 0.1% at maximum power. And that's a little bit higher than the spec, but considering the setup, I think we're okay. So now let's do something. I'm going to disconnect this. So I'm going to take this off here, disconnect this over here, so it's all disconnected. And then I have these two wires right here, and they go to the B jack connectors, speaker B, on the receiver. So if I go down here, you can see speaker B. So what I'm going to do is I'm going to connect this like this. So this is about as direct as you can get. You're coming straight out of the amplifier. And the camera's going to fall over on the stand because I didn't lock it. So it's connected. And then I'm going to select speaker A and B in parallel. So now I have directly coming out of the amplifier through these two wires into the meter. Let's see if that makes any difference. We were right around 0.1. So let's do the same test. So there's 10, 20, 30, 40, and 50. Right about there. And you can see it does make a little bit of a difference. So you do pick up a little bit of noise off of your wiring, and you can see it's 0.07. And again, some of this is the distortion of the test equipment itself, some of it is the wiring, lots of so forth, but again, it gives you an idea. So that knocked off about 0.03% THD by measuring it that way. So there you go. It does make a little difference. But I don't usually worry about that because I know if it's close, I know the rest of it is my test equipment. And I just wanted to show you all that because some of you did comment on that. And that was a great comment. And yes, it does make a little difference. But again, we're splitting hairs right here. I don't think you're going to hear the difference between 0.07 and 0.1. It's going to sound very, very similar. But the amplifier is performing exactly to spec now. Okay, before I do anything more to this receiver, I just want to document this for all of you so you can see another problem that I found in this amplifier. Again, you really have to test everything to know what's going on. So I'm switched now from an 8 ohm load into a 4 ohm load. And what happens when you go into a 4 ohm load, if you remember when we were looking at 8 ohms, it was clipping at the top and the bottom of the waveform pretty symmetrically. It wasn't bad. It was what I would call, a normal, typical amplifier. However, when we switch over to 4 ohm load, I'm not able to get the full power out of what the amplifier is rated at. So it's rated at 65 watts at 0.1% distortion into 4 ohms. Now I can definitely get the 52 watts per channel into 8 ohms, but this thing taps out really early on a 4 ohm load. So I have my dummy load switched down here to 4 ohms. So you can see the switch. And if we go over to this with a lot of reflection on it, if I turn this up, you're going to see at 4 ohms, it clips way early on the top half of the waveform when the bottom half is still very clean. Now, skipping you way ahead, if you look at this oscilloscope, and I'm using multiple test equipment to make this quicker and make it easier for me to demonstrate to you. You don't need all this stuff, but this just makes it easier to record. So if I turn it up here, you can see the same thing happening, where one side of the waveform clips before the other. Now, where am I looking? So if you take a look, where this is happening is all the way back here. So here, this is what goes out to your bias spreader. So you have this Class A amplifier, and this is that transistor that was shorted out and leaky on the other, that we had to replace. And we have a perfect replacement for this, so it's the correct component. There's no difference from the original one as far as specs go. And if I move this over, you can see there's two lines. This line goes directly over to the one driver. This line goes through the bias spreader and out to this driver. So this is your bias spreader circuit, but as you can see at the Class A portion of this, all of your signal is right here. And what's happening is we need a lot harder drive signal to drive these transistors fully into clipping. But unfortunately, what's happening is this transistor is clipping at one side before we get our full amount of power out to this. So what's happening is something is wrong here with the way this circuit is biased. Now, checking all these voltages, they're perfect. However, we just can't get full power. Now, I have a feeling this is something that Marantz may have dealt with. I don't know. Again, I'm not familiar with the 2252 enough to say that. But we can definitely see where in an 8 ohm load it works perfectly. In a 4 ohm load, we would get a lot more power out of this amp into 4 ohms because the power supply is not saturated, is not sagging. We have plenty of latitude on the power supply yet. Big, huge transformer and good sized caps. So it's that this thing is clipping off the top of the waveform, and it's causing that problem. So what I'm going to do is we're going to try to fix that, and then I'll come back and show you what I did when we're done. Okay, the repair's been made, or the mod has been made, and you can see I'm connected back up to the collector of the Class A pre-driver, and starting out in 4 ohm mode. Let's look at 4 ohms. And you can see it's still gonna clip at the one end a little bit more, but look how much more I'm getting before it starts to go. See that? I have plenty of power now, and I'm getting a lot. Remember, this is at 4 ohms, so you're looking at about, we want to get about 16 volts. And you can see the one channel that doesn't have the meter on it is well over 16 volts. And even the one that's clipping with the meter on it, or the scope on it, is 15.7 volts. And if I go over just below clipping and I look over here, I have very good distortion. Remember, all the test equipment is in here yet and everything. And now let's switch back over to 8 ohms and see what we get. Alright, so now we're at 8 ohms load. And you can see now it clips very symmetrically. See that? There's a tiniest little bit of oscillation at the one end, but that's really not going to hurt anything. And looking down here, wait till you see how much power this thing puts out now. There's 50 watts, 60 watts, and just below 70 before it really starts clipping hard. So this thing's got a ton of headroom now. And you can see with a ton of power, I mean, I'm running this thing 65 watts, right, or 55 watts, and you can see the distortion. If I drop it just the tiniest little bit, you can see it goes right down to nothing. And I'm still almost maximum rated power. So all in all, this is good. And just looking at a couple different frequencies, let's go to 20 kilohertz. And I'll have to adjust the scope. Okay, and here's 20 kilohertz. And beautiful looking waveform. Lots and lots of power. Look at that. And let's go down to 20 hertz. And again, I'll have to... There we go. And you can see all kinds of power. And there's 60 watts per channel. It's just starting to distort on the top and the bottom. So low frequency response is phenomenal on this thing. And I'll tell you what, this thing is unbelievable. It's working great. I can't wait to actually connect it up to some speakers and actually listen to it now. Okay, let's take a look at the final modification that I made to get this thing where it needs to be for performance. And really it was pretty simple. I just changed the value of these 4 resistors here. These were originally 100 ohm resistors, and I ended up moving them up to a 250 ohm resistor. And the amplifier is performing perfectly. Frequency response wise, distortion wise, power wise, I'm very happy with it. And this is a really good sounding amplifier now. Actually, this is probably one of the better 50 watt receivers that I've had on the bench now. Still not real happy with the design of the board on this compared to my 2240 or anything like that, but sound wise, performance wise, it's a great amplifier and a great receiver now. So I'm going to show you real quickly what those resistors do and why they needed to be changed. And then we're going to demo. First of all, we're going to listen through the auxiliary inputs, and then we'll use our reverse RIAA module switch on the buffer amplifier I built, and you can check that video out if you want to sometime. And we'll play through the phono inputs because I really haven't tested the phono stage on this since it was recapped and so forth. So let's take a look at the schematic. So one of the problems that I was running into is you have your differential pair, and this side is for your input amplifier, and it's a Class A, Class A amplifier. And then you have the other side that opposes this, and that's your negative feedback. And that's what we use to eliminate or reduce the distortion of the amplifier. Then that goes into another Class A stage, which is this one right here. These are the two channels, right and left. And you come out of the collector is where the output is, and it goes through the bias spreader, and I showed that earlier. And you see this one goes directly to here, the other one goes through the bias spreader and down to this side. And just by its nature, the way this is designed, you only have so much, swing on that signal that you can have here before it taps out. And what was happening was when we went into the 4 ohm load, we needed a little bit more drive out of this transistor to get these drivers to, drive the output transistors to their full power potential. And we just weren't getting it here. And part of it was because these transistors, as they were originally designed, they drew a lot of current, especially when I replaced them with the ones that had a little bit higher gain. Again, these had very low gain. I mean, like somewhere around 20, which is almost like the same gain that you would see on an output transistor. And as such, they had these 100 ohm emitter resistors. And I think just that amount of extra current required, between the base and emitter by our Class A stage was just not allowing enough drive signal to drive this thing properly, especially when we got into, a 4 ohm load. So what I did was I increased the value of these from 100 ohm to 250 ohm. And really a more ideal resistance would probably be a 270 ohm resistor here, but I only had 250s, so that's what I put in there. And they're more than adequate. We probably could get this even a little better, though, if we could get a little more accurate resistance in here. So what that does is that raises the voltage a little bit here, the amount of drive, and it also limits the current somewhat. So you have these transistors run really a lot cooler. When they had the 100 ohm resistors in them, they were okay, but you could feel them getting warm, as you were driving. A lot of times you'll see that in some of these designs. Some of them, they really torture them, and these things run hotter than the outputs. Pioneer is one that's notorious for that. If you ever worked on a SX1050 or a 1250, those driver transistors just get blistering hot. Then the little heat sinks they put them on is just not adequate. So this actually has a couple of advantages because it gives us enough drive signal that we need to drive these outputs, because I get a little more voltage swing here. And it limits the current, so these run cooler. And we still have plenty of current to drive the outputs. So it's a win-win situation. After testing it, I'm very happy with it. It's still tracking very linearly all the way. As you saw, we had a 20 hertz signal, we had a 20 kilohertz, and we did a 1 kilohertz. And I could do the Bodie plot with the MDO 2204, but I don't want to set all that up right now. I really want to get this off the bench. It's been here way too long. But that's what I did. That was the final change. So really, I replaced these two resistors. And I also changed these Miller capacitors over here. And that's really all I ended up doing to get everything really peak performance. Okay, so I'm set up now with the our typical song we use on this channel to test things, the Stranger Danger. And I'm going to play it first through the auxiliary input, and I'll hold my microphone in front of the speaker as I always do. So obviously this is not a good representation, but I can assure you it really sounds good. I'm very happy with the way it performs. So let's start this up. I'll put the volume up a little bit. I'll start our song. Okay, so that sounds really good. Now what I'm going to do is I'm going to go over here and I'm going to go over to my buffer amplifier. It's connected to my computer, and I'm going to flip this, and this is the phono mode. So now this is going to simulate a phono cartridge. And then I'm going to take the leads over here. I'm going to switch us over to phono 1. And let me get everything connected up, and I'll be right back. Okay. So now we're over to phono 1. We're switched in phono mode. And let's see if this performs. Much better. So I'm very, very happy with these couple of little mods. The amplifier now is very clear. I don't hear any kind of sibilance or anything. When you hear hi-hat cymbals or any kind of high frequencies like that, it sounds a lot clearer. We got rid of all that parasitic oscillation. And again, I think that's kind of what they were aiming for when they put the low, really low gain driver transistors, and they fiddled around with some of the capacitor values and things. I think that was part of it, but I think it also affected some other things. But again, neither here nor there. This was what worked for us. Those transistors are kind of getting harder to find, and these ones are very readily available. So this is something that if something fails in the future, a future engineer who will be, repair technician that would be working on this should be able to find the parts to keep this thing running for many years to come. So with that, I'm going to call this one done. And I'm very happy with the way it turned out. It was a lot of work, and I really did this on purpose. I wanted you all to see that when you change things, it's okay to do that, but you have to do the proper testing to make sure that nothing is affected by that. And you can see how just making a small change can make a big change in how something performs. Now, the other problem you're going to run into, as these things get older and older, some of these more exotic components, transistors that have exceptionally high gain or very, very low gain, or something with a strange pinout, JFETs that have high voltage, ranges other than the typical JFETs that you see that are only good for 30 volts or so. All those kinds of components are going to get harder and harder to find. And we're going to have to look at things like this as a solution to be able to keep these things working the way they did when they were brand new. It didn't really change this amplifier. This is what it's supposed to do, how it's supposed to work. So we really didn't change the character of the amplifier, but we made it future-proof, and we kept it working like it would have been working when it was brand new. So anyway, I don't know. I had a good time with this project. I hope you learned something. I know I did. I always do whenever I work on something new. And, well, I'm going to get this one out there, and it's probably going to go to some happy owner and be sold. And the next project that I can't wait to start is going to be for my personal collection. And if I get this up to where I want it to be, it'll probably be my main listening system. I don't know. But anyway, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care, everybody. Bye-bye.